Okay, welcome back to our lecture on quantum information theory. Let me first briefly recap what we did last time. So, in the last session, we usually considered a communication between Alice and Bob. So suppose there's Alice communicating with Bob, and suppose that Alice, for the communication, she uses some ledgers made out of the quantum states rho 1 to rho n, which appear with probabilities p1 to pn. So what Alice does is she samples from this probability distribution, and then given the state that she draws, she sends this one to Bob, right? So we can associate this with a random variable, say capital X. And okay, what Bob does is Bob wants to know the outcome of this random variable, right? So the state that he receives is rho equals to sum over x px rho x, and he performs a measurement. And what he wants to do is, as I just said, he wants to find out the value of x, right? So what he wants to do is he wants to find out which rho x he got. And in order to do so, what he does is he performs a PUVM, which is defined by some measurement operators EY. And this measurement then gives rise to outcomes which appear with the probabilities PY, right? And this probability distribution, which is the outcome of the measurement, can now be associated with the random variable y. Okay? And last time we also then argued that the information that Bob has about the random variable x can be quantified by the mutual information h of x and y, right? And what Bob wants to do, he wants to choose this measurement such that this information is maximized, so such that the mutual information is maximized. Okay? And this defines the accessible information of Bob. So we define the accessible information of this ensemble E. So we can call this ensemble E. And this was given by a maximization over all PUVMs, and we maximize the mutual information. Right? So this is the maximal information that Bob can get about the outcome, about the random variable x. Now, given that we have here maximization, it is often very hard to calculate here the right-hand side. So to calculate this accessible information. And as a next step, what we did is we found that there is a bound, there's an upper bound to this accessible information, and this was the so-called Holevo bound. So the Holevo bound gave an upper bound of this accessible information of Bob, and the theorem of the Holevo bound was as follows. I mean, it was that the accessible information of this ensemble E is bounded up from above by S of rho minus sum over x px S of rho x, where S is the von Neumann entropy. Right? So with this, we now have a upper bound which we can easily evaluate, right? Because we have now the upper bound in terms of von Neumann entropies, and we have no maximization anymore. Okay? Doesn't mean that the upper bound is always tight, but in some instances it is tight. But as you will do in the exercise, there you're going to study one incidence where the upper bound is far away from the actual accessible information. Right? So keep in mind this is simply a bound. However, with this bound at hand, we can now really try to figure out what's the worst case, so to say. And I'd now like to continue with doing an example. So let's do an example of such a procedure. And suppose that Okay, suppose now Alice draws from the states 0, 0, 1, 1 with probabilities P1 equal 1/2 and P2 equal 1/2. Sends this to Bob. However, there's some noise in this channel, in this quantum channel that they use. So there's noise such that Bob receives, instead of the state rho equal to 1/2, 0, 0 plus 1/2, 1, 1, he receives the state E of rho. And for the noise, we now assume simply amplitude damping, right? And this is then such that we get 1/2, 0, 0 plus 1/2. And now amplitude damping means that the amplitude of 1 is damped by a factor of 1 minus gamma. So gamma is the strength of this damping. So we get 1 minus gamma 1, 1 plus gamma 0, 0. So with strength gamma it is damped. So this is the state that Bob receives, and what he does is he performs a measurement. So this is Bob performing a measurement, similar as before, with some POVM, which gives rise to the probability distribution Py, which we can associate with this random variable y. And what we want to figure out now is how much information got lost due to the noise in the channel, right? Because now, let me stress that what Alice sends are orthogonal states, meaning that if Bob performs the right measurement, namely in the spaces, then he can get all the information if there was no noise. However, due to noise, it now happens that Bob gets not necessarily orthogonal states, meaning that some information got lost. Okay, so what the state is that Bob receives, if we calculate this, is now it's 1 plus gamma half 0, 0 plus 1 minus gamma over 2, 1, 1. Okay, this is what Bob receives. And let's calculate now. The Holevo information, namely this upper bound of this accessible information. So what we ask is how much information got lost due to the noise, due to the noisy channel. And for this we calculate the accessible information, which is bounded from above by this Holevo information, which we call chi. And this was, as it's written down here, it's the von Neumann entropy of rho, and rho is now this state here, namely E of amplitude damping of rho. This is what he got. And then we have minus, and then 1 plus gamma over 2 von Neumann entropy of 0 plus 1 minus gamma over 2 von Neumann entropy of 1, right? There's a bracket missing. And the first thing we see is that the von Neumann entropy of a pure state vanishes, right? So this is 0. So we are left with this expression here. And this expression we can calculate using the eigenvalues of this state. And here we can read off the eigenvalues. One eigenvalue is 1 plus gamma over 2, and the other one is 1 minus gamma over 2, right? So, meaning this is simply minus 1 plus gamma over 2 logarithm of 1 plus gamma over 2, and then minus 1 minus gamma over 2 logarithm of 1 minus gamma over 2. So this is equation 3.175. Well, and with this, we specified how much information Bob can gain about this random variable x, right? Now, the information which got lost is then the information in the case of no noise minus the information that Bob can gain. Okay? So hence, we lose chi of e in the case of gamma equals 0 minus chi of e bits of information, which is equal to 1 minus chi of e bits of information. Right? So in the case of no noise, there's exactly 1 bit of information, and then we have to subtract the Holevo information such that we get the information which is lost due to the noise in the channel. Okay? So this is the example that I wanted to do. And in a sense, this gives a bound on how much information is lost. Right? Okay, so much to the topic from our last lecture. And now today I'd like to start with a new section, namely with a brief introduction into entanglement theory. And this is gonna take some more time, so possibly until the end of the lecture. So at least it will take this week. And this is now section 3.4. A brief introduction into entanglement theory. So in the beginning, let us first recall what we already learned about entanglement. Okay? So in the first chapter of this lecture, we introduced entanglement of bipartite pure states, right? So you possibly remember that we defined entanglement of a bipartite pure state such that a state which cannot be written as a product state was defined as an entangled state. Okay? Let me stress that this is only valid in the case of bipartite pure states. So let's briefly write this down. It was so in section 1.4.4 we defined a state psi living in the composite Hilbert space HA tensor HB to be entangled if it cannot be written as a product state psi A tensor psi B for any choice or for any choices of psi A in the Hilbert space HA and psi B in the Hilbert space HB. Okay, so you can see this as kind of we defined an entangled state as being not a product state. Okay, but now to be more precise, what we actually wanted to say is that we want to define an entangled state as a state whose correlation cannot be described by classical correlations. Okay? So this is what we actually want to say. And the reason why this comes out, I'm going to say the reason for in a moment. So let me write this down here. So more precisely, we call a bipartite state entangled. If it contains correlation, if it contains correlations between subsystem A and B, which cannot be described by classical correlations. So, well, this statement here that we call a bipartite state entangled if it contains correlations which cannot be described by classical correlations is for bipartite pure states. So for pure states, this is equivalent to saying that we're having not a product state. The reason is that for pure states, we cannot describe classical correlations. Right? So remember that classical correlations we describe by mixed states, right? And whenever we describe the classical correlation, we needed a mixed state, meaning that pure states cannot describe classical correlations. And this means any correlations described by a pure state must be purely quantum. And only by this reason could we define a state to be a pure state to be entangled if it is not a product state. Okay. If we now go to mixed states, it's much more involved, because in the case of, if you want to describe entanglement of mixed states, then we really have to distinguish whether these correlations are now quantum or classical correlations. So for mixed states, we cannot say if it's a product state, then if it's not a product state, it's entangled. This is not, we cannot do this for mixed states, right? So let's write this down. For bipartite pure states, this is equivalent to being not a product state so the reason is that pure states cannot describe classical correlations. Between A and B. Okay, such that all correlations of a pure state or of a bipartite pure state must be purely quantum. So, and this is due to classical correlations. Being described by mixed states. So remember the example of this correlated SOCs, right? There we described the quantum count, so the quantum state of such a scenario where we have classical correlations as a state rho, which was with probability 1/2. We had that the left SOC was dark and the right SOC bright. Okay, and with probability 1/2, the left SOC was bright and the right SOC was dark. So this is a mixed state and describes classical correlations. Now, so with this we see that entanglement, if you go beyond pure states, then entanglement cannot be described by not being a product state. So hence, if we go or hence beyond pure states, entanglement cannot be described So hence, beyond pure states, entanglement cannot be described as not being a product state. So we have to come up with some more precise criterion to describe whether a state is entangled or not. And this is what we're going to do now. And the approach is now as follows. So what we're gonna start with is a state without any correlations. So a product state, right? And then what we do is we ask which operations can we do on this product state such that no entanglement is generated. Right? And with this, we then figure out how states must look like which are not entangled. And those states we will see in a bit, we call them separable. And then we can define entangled states as states which are not separable. And with this, we found two things. First, we figured out, or we're going to figure out which transformations do not generate entanglement. These are the so-called LOCC transformations. And then with this we then can define what an entangled state is, namely not the separable state. Okay, these are the two things that we're going to do next. And this is subsection 3.4.1, which is LOCC, entanglement, and So let's start from the bipartite state. Rho AB, which is a density operator in the Hilbert space HA tensor HB without any correlations. Between subsystem A and B. So without any correlations means neither quantum nor classical correlations, right? And then it's a product state, rho A tensor rho B. So we start with the state. And we ask how it changes if Alice and Bob perform operations. On their system which cannot generate entanglement. Or cannot generate more than classical correlations. Okay, so let me say it again. We start with a completely uncorrelated state, which we can write in this product form. And then we say Alice is in possession of rho A, so it's somewhere in this lab of Alice. And Bob is in possession of rho B. It's somewhere else in Bob's lab, right? Completely uncorrelated. And now we ask, okay, what kind of transformation can Alice and Bob do such that there is no more than classical correlations. Okay? So the first thing, of course, what we can come up with is that Alice and Bob perform local operations. Well, if Alice does something in her lab and Bob does something in his lab, then of course there can be, it doesn't change anything in terms of their correlations. Okay? So meaning that local operations cannot generate entanglement. So this is our first operations that we consider. So first we note that any operation which acts locally on each subsystem cannot generate correlations. Okay, these operations are described by the operation elements so we have EJ acting in Bob's lab and FK Alice or Alice lab and Bob lab, and we consider the set of all these operations where the set goes over all J and K. And those operations, they map product states to product states. So these operations map product states to product states. So we have the operation of a local operation on row A tensor row B is then given by sum over j ej row A ej dagger tensor sum over k fk row B fk dagger. So what we see is that those local operations map product states to product states, so no correlations are generated. Hence, no entanglement is generated. Well, now we can ask, okay, what other operations can Alice and Bob perform, right? So for this, suppose that Alice is in her lab and she's doing such a local operation. For example, this can be a measurement, and then she gets, for example, measurement outcome J, and what she does is she calls Bob via a classical channel. So she calls him and says and tells him the outcome. And what Bob does is he now performs a measurement on his system based on the outcome of Alice, right? And by this, what they did is they generated classical correlations, right? So suppose that Alice and Bob, they can also communicate via a classical channel. So in addition to performing local operations, we suppose that they can also communicate via this classical channel. And then obviously this can generate no more than classical correlations. Or this cannot allow Alice and Bob to generate more than classical correlations. So this means that the resulting state under local operations, and classical communication, which we abbreviate by LOCC, must be, so that the state must be unentangled. So let us suppose that we start from such a product state, and let's see how this state looks like if Alice performs a measurement and communicates the outcome of her measurement with Bob, and Bob then performs a measurement conditioned on this outcome. Let's see how this looks like. So suppose Alice performs a local measurement or a local operation. You can think of a measurement, and this local operation is then EJ tensor identity, because there's nothing happening in Bob's system. And she sends the outcome to Bob. Who then performs the local operation FJK conditioned on Alice message. Okay, so note that the notation is such that FJK is the operation element that Bob performs, so the Bob's case element that he performs if he gets from Alice the message J, right? So here the set only goes over all K. And and this set depends on J. Conditioned on else message. Okay, this results in the following state. So this is local operation classical communication. Now note that this is performed on the product state, row A tensor row B. And this is then sum over JK, and then we have EJ row A, EJ dagger. So this is first Alice performs this operation, which is described by this operation elements EJ, right? And then she communicates the result with Bob, who then performs this the operation FJK on his system. And now note that this is dependent on the outcome of Alice, right? So with this, we have now introduced some classical correlations. So this cannot be written as a product state anymore, because we now have classical correlations. So this procedure introduces classical correlations between Alice and Bob. And the reason for this is that Bob's operation is conditioned on what Alice tells him. Okay, that's the reason that there are now some classical correlations. So we can now, okay, let me draw a picture here of this scenery. So we had Alice, which was possession of the state row A, and here's Bob, in possession of the state row B, and then so we had the state row AB, and what Alice did is she performed a local measurement, okay? Namely, she performed this measurement EJ, so 1J, okay? And then she communicated this result to Bob, who then, so via classical communication, and then Bob performed this measurement on tensor FJK conditioned on this message. Okay, this is what we did so far. However, now Bob can also communicate his result to Alice, right? And Alice can again perform a measurement on or a operation on her system conditioned on what Bob's message is. Okay, so there can be now again classical communication, and Alice performs this measurement EJKL, which now depends on J, K, and K. And after Alice performed this operation, I mean, she can again do classical communication to Bob, who then again performs a conditioned operation. And those rounds of local operations and classical communication can, in principle, be infinitely many. Okay, so there can, in principle, be infinitely many such rounds. And the set of all these operations which you can generate via this LOCC are called LOCC operations, right? So we're gonna define this in a second. But it's just that you have in mind how LOCC actually works. So there can be finitely many rounds, but in principle there can also be infinitely many rounds of local operations in classical communication. Okay, let's define this. So after arbitrary many rounds, which are possibly infinitely many Alice and Bob, they end up with the following state. So, and by these dots, I mean that there are simply some more operational elements coming in, depending on how many rounds of LOCC they use. So, and this, now there's one thing that I'd like to stress, that this procedure of LOCC is fundamental for entanglement theory. The reason is that it defines the set of operations under which entanglement cannot increase, right? So we said that if we have local operations in classical communications, we cannot introduce more than classical correlations. And this says that entanglement cannot increase under LOCC operations. And that's why this is fundamental for entanglement theory. And whenever you study entanglement theory, you will come across LOCC operations. Okay, so this procedure of LOCC is fundamental for entanglement theory. Since it defines the set of operations under which entanglement cannot increase. So let's now properly define LOCC, which is a definition 3.17. It says that the set of local operations in classical communication on a bipartite state. So we are defining it here for a bipartite state. However, it can be defined similar for a multipartite state, but we simply restrict here to bipartite states for the reason of time. But once you understood this for bipartite states, it's easy to generalize this. So we have that the set of local operations in classical communication on the bipartite state rho is defined as the set of maps E LOCC acting on rho AB, which is sum over JKL, and then we have E JKL tensor identity, then identity tensor F JK, and then identity tensor EJ, and then rho AB, and here the Hermitian conjugate tensor EJ dagger. Then oh, now I did a mistake. EJ tensor identity. EJ dagger. Identity FJK and EJKL tensor identity dagger. So where EJKL are local operations on subsystem A, And one tensor F K J to K are local operations on subsystem B. Okay, so this is now the formal definition of LOCC. And note that here on the side we considered particular a product state as the argument. And now this equation 3,179 is the same as 3,180. However, what we considered here is a general bipartite state as an input, right? Otherwise, it's the same. And with this, I think it's a good point to do a break. And after the break, we then gonna see which states we can generate via LOCC if we are starting with a product state, meaning that which state can we so which states do we get via LOCC, and those states must be not entangled, right? And then we can define entanglement as those states which cannot be generated by LOCC if we are giving as an input a product state, right? This is what we're going to do after the break. Okay. Let's continue with the second half of the lecture. So in the first half, we started with our chapter on entanglement. And in particular, what we did is we defined the set of local operation and classical communications. And what we started with was a product state, of a bipartite product state, rho A tensor rho B. And we've seen that if we act with local operations and classical communications, we get something like this. Okay? And then there can be up to infinitely many rounds of LOCC. However, what we're gonna do next is we take a closer look at the state. And what we see is that this can be written in a particular form. So with the moment of thought, we see that this can be written a little bit simpler. So after a moment of thought, we see that the state from this equation 3,179 can be written as follows, namely as E LOCC of rho A tensor rho B being a sum over J, and then we have some probabilities Pj, and then states rho Ja tensor rho Jb. Where these Pj's are probabilities. And they're summing Pj are probabilities. Satisfying that if we sum over them, we get 1. So let me first do an example. So you possibly don't directly see it, right? So let me do an example of the state if there's only a single round of LOCC. So for example, the state so it was LOCC1, where we had a single LOCC round, which was written as sum over jk ej row A ej dagger, then tensor fjk row B fjk dagger. So this we've seen before for a single round of LOCC. So for example, this state for this state we have the probabilities Pj being equal to trace of Ej row A Ej dagger, and those states row A J are equal to Ej row A Ej dagger divided by Pj, and the states row Bj are equal to sum over k, and then we have fjk row B fjk dagger, such that now if we write this down, sum over j pj row aj tensor row bj is equal sum over j. Now we can plug this in. Here the probabilities pj, and then we have ej row A ej dagger divided by pj tensor sum over k fjk row B fjk dagger, which is exactly the state here. Okay, so these probabilities cancel. So this is sum over jk ej row A ej dagger tensor fjk row B fjk dagger. Okay, I hope that you see it. That we can write the state now here for a single round of LOCC in this form, right? And in general, we can, for an arbitrary number of rounds, we can always write the state in this form, so, as given here by this equation 3,181. And the states, so what does it tell us? It tells us that given a product state, meaning a state without correlations, meaning that LOCC operations can only transform into states of this form. Okay? Meaning that states of this form can have no more than classical correlations. Okay? Let's write this down. That is, so we found that via LOCC which cannot generate entanglement, only states of the form 3,181 can be generated. Where the probabilities So those probabilities Pj here, they account for these classical correlations. And the states have a particular name, namely they're called separable states. Okay, this defines now the separable states. It's definition 3.18. A state rho A, B. Now I consider a multipartite state because I want to define this in a more general setting. But usually what we consider are bipartite states. But let me define this for a multipartite state, leaving the composite system rho A, tensor rho B, tensor, HA, HB, HC, and so on. And this is said to be separable if it can be written in the form that rho A, B, C, and so on is given by a sum over the probabilities Pj and then we have tensor rho Aj, tensor rho Bj, tensor rho Cj, and so on. So with these Pj's being probabilities summing to 1. Okay, so now you know what kind of states we can generate via LOCC given a completely uncorrelated state. Namely, we can generate separable states. And as we defined the LOCC operations as those operations which cannot generate entanglement, then we can now define a state to be entangled if it is not a separable state. Okay. So this definition allows us now to properly define entanglement. And it's definition 3.19. Says that all non-separable states they are said to be entangled. Okay, now we know which states are entangled, so at least we have a criterion such that we can say whether a state is entangled or not. Now let me give some remarks here. The first remark is that if we're given a a separable non-entangled state, then by LOCC we cannot generate entanglement. So we cannot generate an entangled state if we are given a separable state, right? And this is simply by definition. So note that given a separable non-entangled state by construction LOCC operations cannot generate entangled states. And then, second remark, we can now ask, suppose we are given such a completely uncorrelated state as we started with, so this product state, can we now ask, can we generate all separable states via LOCC, given such a completely uncorrelated state? And the answer is yes. So, given a product state, rho A tensor rho B tensor rho C and so on, can we generate all separable states via LOCC? And the answer is yes. And we can see it as follows. So suppose we start from the state and Alice, she samples from the probability distribution Pj and sends her outcome via classical communication to the others, who then create the state rho xj via local operations resulting in the state sum over j pj rho ja tensor rho jb and so on. So meaning that with this protocol we can generate all separable states, right? And with this we see that by given such a product state we can generate all separable states via LOCC. Okay, so the next thing I wanna briefly discuss is, let's come back to this definition of LOCC. So it's not the definition here, but it's here. It's so we see that already by this, if we have an LOCC operation on some state, it can get very complicated at some point because we must allow for an infinite number of LOCC operations, right? And if you do calculations, especially if you want to prove something in entanglement theory, this can become very quickly very complicated. However, there's a trick that one can do, namely, instead of considering those LOCC operations, one can consider the so-called separable operations. It's a proper superset, meaning that all those LOCC operations are contained in the set of separable operations. But since I said it's a proper superset, it means that the set of separable operations also contains more, right? So if you're working with in entanglement theory, often it's good that instead of considering this complicated set of LOCC operations, you first consider the set of separable operations, which is, from a mathematical point of view, a bit easier to handle. And then once you got a result, you have to check whether this result also holds if you reduce your set of operations to the LOCC operations. Okay. So I think it becomes clear in the moment when we write it down. So, so dealing with LOCC operations can quickly become complicated. A common trick is to consider the set of separable operations which we abbreviate by SEP instead. Which is a proper superset of LOCC. This means that LOCC is a proper subset of SEP. Okay, so this is and then reducing to LOCC. So this means that all LOCC operations are contained in the set of separable operations, but the set of separable operations is larger than the set of LOCC operations, right? So there's no equality here. And the set of separable operations is defined as follows. So this definition is 3.20. The set of separable operations on a bipartite state rho AB is defined as the set of maps with operation elements Ej, Fj acting as E sep on row AB is equal to sum over j, and then we have Ej row, Ej tensor Fj row AB and Ej dagger tensor Fj dagger. Okay, you see that if you compare with the definition of LOCC operations, it is similar, but it's in the end it's different, right? And it takes a easier form. And now I think you see that why it is sometimes better, or it's easier to start with calculating with separable operations. Suppose you do a proof, you want to prove something in entanglement theory, then often it's good that you start with separable operations. And once you've shown a result, what remains to do is you have to reduce those allowed operations to LOCC operations, right? The reason is that it's a proper, the separable operations are a proper superset of LOCC. Right. Okay, then here, let me also say a few remarks to separable operations. The first one is that separable operations map separable states to separable states, similar as LOCC operations. So note that separable operations map separable states to separable states. And then secondly is just like LOCC, separable operations acting on product states cannot generate entanglement states. This actually follows directly from the first remark, right? Because it maps separable to separable states, meaning that if it acts on product states, we cannot generate entangled states. And as a third remark, since LOCC is a proper subset of SEP, so we have LOCC is a proper subset of SEP. There are operations in SEP which don't belong to LOCC. Hence, while we require entanglement, to be non-increasing under LOCC. The same is not necessarily true for separable operations. So remember that the LOCC operations are those which cannot generate entanglement. So meaning that under LOCC operations, entanglement is non-increasing. However, since the separable operations are superset, so there are operations in SEP which are not in LOCC, meaning that there can be operations in SEP where it does not hold that entanglement is non-increasing under such operations. And indeed, there are people which found such instances. So the same is not necessarily true for SEP operations. Okay, so with this we've seen two classes of operations, and the class of operations which is particularly interesting for us is the local operations and classical communications. And the next question that we want to address is how can we describe whether we can go from one state to another state via LOCC. Okay? So suppose that we have two states, rho and sigma, and we now know that under LOCC operations we cannot generate entanglement, right? So we now ask, under which conditions can I transform rho into sigma via LOCC? Okay. And now the first and easiest instance applies if I can perform rho into sigma and sigma also into the rho back. Okay. If I can do this, then this can only be if I perform local unitary operations. It must be unitary because I'm transforming back and forth, right? And it must be also such that I'm not losing entanglement, right? Because if I go first from rho to sigma and then from sigma to rho via LOCC, then I cannot lose entanglement via these operations. And this means that I need local unitary operations. This can only be if I have local unitary operations, right? So this is the first thing that we're gonna define, such locally unitary equivalent states. And then we ask only the one-way direction. Okay, under which condition can I transform rho into sigma? And there we're gonna start with discussing this scenery for pure states, okay, in order to simplify this. So this is now section 3.4.2, transforming bipartite pure states via LOCC. So first, if a state rho can be transformed into sigma via LOCC, then rho must be at least as entangled as sigma. Well, this is simply by the fact that we defined those LOCC operations as the operations which are non-increasing, which do not increase entanglement, right? So as a consequence, if the LOCC operation is invertible, which is the case if and only if it corresponds to local unity operations, then rho and sigma must have the same amount of entanglement. And those local unitary operations, with this we can now define the so-called local unitarily equivalent states. Okay, this definition 3.21. And the reason that we define it is because of this last statement that under local unitary operations, so if two states are connected by local unitary operations, they must have the same amount of entanglement, right? Meaning that all states, if I have the states which are connected by these local unitary operations, then all of them must have the same amount of entanglement. And in order that we can deal with this, we define them. So we give it a name and we define them as the local unitarily equivalent states. So we have two states, rho and sigma. Or let's define it in a larger Hilbert space, HB, tensor HC, so on, are said to be local unitarily equivalent. If there exist local unitary transformations UA tensor UB tensor UC and so on, so with UX unitary, such that rho is equal to UA, UB, UC, and so on. Then we have our state sigma and UA dagger, UB dagger, C dagger. Okay, so with this definition, we now defined what we mean by local unitary equivalent states. And let me say it again, this definition is important because we know that under such local unitary transformations, the entanglement, the amount of entanglement of these states does not change. Okay, so we're gonna use this the next time when we consider the case or when we consider under which conditions we can transform rho into sigma via LOCC. Okay, and next time we start with this and we consider their bipartite pure states, and we will see that this simply relates to the Schmidt coefficients, which we know from the Schmidt decomposition. Right? And this we're going to do next time. So with this, I'm at the end for today, and I see you next time on Thursday.